Now the last part, difference in displacement due to rotation only. Okay. Okay. What is shown here? The same plate, just rotation, which we call as rigid body rotation, the entire body just rotates. P Q R S is the initial state, P star, R star, Q star, S star is the final state. If you look at this, there is no change in length between P R, P star, R star, and the angle R P Q is equal to angle R star P star Q star, no shear strain also, only rotation. Okay. And this is a component you want to separate out. Remember, we already separated out translation, but difference in displacement still includes rotation. We are going to separate it out. So, let us see what is this, what does this component contribute. Look at this, S has moved to S star, there is a difference in displacement. The reason is rotation. We are evaluate the fine expression for that. Now, once again this figure is we have discussed already in the context of deriving relationship between normal strain, shear strain and rotation also we derived in terms of displacement gradient, same figure here as we have seen in the previous slide. Now, when we derived that omega xy is equal to alpha is equal to dou uy by dou x, and alpha was rotation in the anticlockwise direction. Then we also derived for rotation for this element P r to P star r star, and the relationship was omega xy is equal to beta, but we said because it is in initially P r was this, initial plate was P Q R S. So, P r rotated in the clockwise direction, because we have taken into account the direction clockwise is negative, we added a negative sign and we related omega xy is equal to minus beta is equal to minus dou ux by dou y. Okay. Now, if you write in terms of difference, omega xy is equal to delta uy by delta x and omega xy is equal to minus delta ux by delta y. Is it okay? Now, these relationship, what do they tell you? Omega xy is a rotation and that is related to difference in y displacement for particle separated along x axis by delta x. That is what we have here, P and then S. Once again there is no movement displacement of P, and so we can apply this relationship for the present case for difference in displacement between P and S. Similarly, what does this tell you? Second expression tells you the relates the rotation omega to the difference in x displacement for two particles which are separated along the y axis by delta y. That is what we have here also, P and S separated by delta y along the y axis. Okay. So, now what we will do is apply this expression for this triangle. What is that triangle? Before that, just like in the previous case, this angle is omega xy, this angle is omega xy. Similarly, this angle, all angles are omega xy, just rotation. So, the angle between the lines, corresponding lines between the initial state and final state, all of them are omega xy. Now, we will apply this this first relationship, and we will apply that for this triangle. As earlier, right now does not look like a triangle. In the limit of omega xy very small, you can approximate that to a triangle. Okay. Now, from that triangle you can write omega xy is equal to delta uy by delta x, okay. And if we will apply this relationship for this triangle, where we relate omega xy to delta ux and delta y. Okay. Now, we have discussed the negative sign. Whenever you talk about delta y, it is higher y minus lower y, you are along the y axis. Okay. So, there is no ambiguity. When you talk about delta ux, it is always final state minus initial state, that is what delta ux represents. in this particular example S star is the final state, S is the initial state and that has moved along the negative x axis. To account for that we have the negative sign. So, if it is both along the positive axis respective axis, then negative sign is not required, as we have in this case. In the case of delta u by delta x, S moved vertically up. So, it is along the positive y axis and of course, x is along the positive x axis, but when you take the second expression delta y is still along the positive y, always it is y 2 minus y 1 or y higher minus y lower, but S moves towards the negative x axis and so the negative sign takes care of that. Now, as usual we will use these expressions for writing expressions for delta u y and delta u x. What do they represent? They represent difference in y displacement and x displacement because of rotation only. Okay. So, first write for x direction. So, difference in x displacement, okay, due to rotation only, Okay. So, we use the second equation, this equation, okay, delta u x rotation only is equal to minus omega x y delta y. Okay. Let us use the first equation and write expression for difference in y displacement due to rotation only. So, as usual the nomenclature has been made very clear. The first says delta u x difference in x displacement due to rotation only is equal to minus omega x y delta y. Second equation is difference in y displacement due to rotation only written as omega x y delta x. Okay. Just as a quick check, in this particular case is omega x y positive or negative? Is omega x y positive or negative? Anticlockwise rotation, omega x y positive. Okay. So, now let us take this equation, omega x y is positive, delta y is positive, delta u x is negative, delta u x is indeed negative. Okay. We should get a negative difference in x displacement. Okay. So, that is only cross check. In fact, we written the negative sign taking into account the x displacement, just as a quick cross check, or omega x y is positive and delta y is anyway positive. So, if you substitute delta, the difference will be negative, which is in line with our movement of S to S star along the negative x axis. Now, of course, for the difference in y displacement, that is very clear, omega x y is positive, delta x is positive and S moves along the positive y axis. Okay. So, now let us summarize the expressions which we have derived in the previous slide for difference in x displacement, difference in y displacement due to rotation only. Okay. Okay. Now, let us fill up this table. We have filled up normal strain, we have filled up shear strain, they are not shown just for clarity. Now, we have to fill up this rotation only. Now, just like for shear strain, when shear strain happens, it contributes to x and y displacement. Similarly, when rotation happens in x y plane, it contributes to x displacement and y displacement. Okay. And so, you will have one entry for delta u x, one entry for delta u y, and that is what is shown here. So, delta u x entry is this minus omega x y delta y, and delta u y entry is omega x y delta x. Of course, you have to be careful about sign. One is minus omega x y delta y, other is plus omega x y delta x, and when you repeat, when you write analogously for the other directions, we have to take care of the sign as well. So, now consider rotation y z plane, it will contribute to the y direction, and that is this term. It will contribute to the z displacement, that is this term. Now, consider rotation in the zx plane, that will contribute to z displacement, will also contribute to x displacement. So, now we have filled the last column also. based on rotation in the x, y, y, z and z x planes. Okay. So, rotation in the x, y plane results in difference in the x and y displacement. Okay. So, let us all put together all of them. Okay. The individual figures are shown here, the individual tables are shown here, the bottom of the slide. The first figure is for normal strain, corresponding table, second figure for shear strain only and the corresponding table, third figure is for rotation only and the corresponding table. Okay. Now we can fill the entire table, we said we are proceeding towards that, and so what is it I have done? Written delta u x, this delta u x what is written here is the total difference in displacement, that is the left hand side. Now the right hand side, you have 3 columns for let us say normal strain only, shear strain only, rotation only, and picked up components from here, epsilon x s delta x is written here, and then taken the first row here and these components are written here and these terms are written here. So, this full table is just a combination of the 3 separate tables what I have shown earlier. Okay. And what is the other way of looking at it? If you focus on a particular row, what can be physically told? The total difference in x displacement is or has contributions from normal strain, shear strain and rotation, that is what we said. Okay. The displacement has an additional contribution, translation, we have taken care of that. Difference in displacement does not have that component, translation, it has rotation, normal strain and shear strain. Okay. Now, what we will do is we are proceeding towards getting the relationship between dx, dy, dz and dx, dy, dz in terms of displacement gradient in the second way, which is more geometrical way, and that is what we will do now, that is the last step. We said we will derive the displacement gradient in 2 different ways. The first one was more mathematical, the second one is more geometrical, and that is what we have done now. So, now we are at the last step where we are going to arrive at the expression. So, now what we do, okay, I come back to differential, okay, because our expression was in terms of the displacement gradient expression was in terms of differential. Let us just come back in term, though this table is in terms of difference, I am writing in terms of differentials. Okay. So, look at the nomenclature very clearly written here, the left hand side is difference and displacement, okay, and then the bracket says total and difference in displacement along x direction. So, left hand says difference in displacement or differential in displacement, and that is a total difference in displacement. Right hand side we have difference in displacement due to normal strain only, difference in displacement due to shear strain only and difference in displacement due to rotation. What is that we are going? We are going to do sum up all the components, all the terms in the first row, okay. All of them correspond to difference in x displacement coming from contributions from normal strain, shear strain and rotation. We are going to sum up all of them. Let us do that and see what do we get. Okay. That is the first term, normal strain, these two put together shear strain, these two put together rotation. Just want to mention, if you take x direction, let us say for shear strain, it has contribution from epsilon xy, shear strain epsilon xy is gamma xy by 2, comes from shear strain xy plane. It also has contribution from shear strain zx plane. Okay. So, if you observe these two terms, difference in x displacement because of shear strain has further two components, one from shear strain in xy plane, shear strain in zx plane. Okay. Similarly, for rotation, if you say the difference in displacement x direction has two components, one coming from rotation xy plane other coming from rotation in zx plane. Okay. Now, what we will do, so this equation is just sum of all the terms in the first row. We will express them in terms of displacement gradients. Okay. So, let us do that. Du x is equal to epsilon x x is nothing but dou u x by dou x, you will understand the color shortly. Okay. And epsilon x y, remember, is shear strain by 2, please keep that in mind, usually it is a cause for confusion. Epsilon x y is gamma x y by 2, this is gamma x y multiplied by a half. Okay. And then epsilon z x, this is gamma z x divided by 2, and omega x y, this is omega x y, remember we also discussed how to remember omega x y, the same term gamma x y, and the change of sign, and this also has a half a negative sign, and then of course corresponding expression for the zx plane with a negative sign here, but this is positive. So, now let us look at the color code here. If you simplify this, all the blue terms remain dou u x by dou x, okay, as such, and if you sum this dou u x by dou y and this dou u x by dou y, minus into minus is plus, and you have a half here, you have a half here. So, that becomes dou u x by dou y into dy, and then if you sum up these two terms dou u x by dou z, dou u x by dou z, half half is 1, you get this term, and the red terms cancel each other. You have dou u y by dou x here, you have minus dou u by dou x, that cancels out, dou u z by dou x and minus dou u z by dou x cancels out. Okay. So, only the blue terms remain, and similarly we can get derive for other directions for du y and du z as well. Okay. So, I think now these expressions are familiar to you, the same expression is what we derived earlier more mathematically, okay, and that is what we are going to see in the next slide. So, if we summarize all this, we will summarize all the total difference in displacement, these are same as what we have seen in the previous slide. Similarly, the third direction, and then we will arrange in a form of a matrix, that is what we did earlier also. Okay. Du x, du y, du z is equal to the displacement gradient tensor, the same tensor has come up again. Okay. And then the vectors of d, the column vector of dx, dy, dz, which is displacement gradient tensor. Okay. Remember, this slide is same as earlier slide, only the title is different. Earlier title was displacement gradient tensor obtained more mathematically, but right now this is obtained more geometrically based on the components. Okay. Just to recall, these are the slides which we had earlier, where we considered 2 points separated by dx, dy, dz, and then we first took off translation by looking at difference in displacement. Then we wrote expression for difference in displacement first vectorially and then along x direction, and got this relationship by expanding in Taylor series or expanding this total differential in terms of partial derivative. And we look at the previous slide what we had and this slide are same, the title is different, because the way in which we arrived, this is the first way, what we have done right now is the second way. Both result in the same expression, same matrix equation or same set of equations in two different ways. Okay. So, let us write down the relationship which we have got in two different ways. Physical significance is same. What does this mean? If you have got the same expression in two different ways, what are the conclusions? Okay, that is what we are going to discuss now. Two different ways. First one, mathematically from total displacement. Okay. Second one geometrically from components of total displacement, that is what we have done. Okay. What is the implication? That is the statement now. Normal strain, shear strain and rotation completely specify the total displacement. What does it mean? If you are considering the difference in displacement, when I say total displacement, total difference in displacement, we made a statement that it has three components: normal strain, shear strain, rotation. We are proving it now. There could be other terms also, other components also, but this proof tells you that we consider only three ways: normal strain, shear strain and rotation. By considering the individual components, we get the same expression what we had taken earlier by considering total displacement, which means that normal strain, shear strain and rotation completely specify the total displacement or difference in displacement. That is an important conclusion. Initially we made a statement that I am going to consider only normal strain, shear strain only, rotation only, but why should I consider only these three? This is the conclusion. If it is enough if you consider those three, you can arrive at the same expression, which implies that those are the only three one or two strains and rotation to be considered to arrive at the total displacement. Okay. That is a conclusion which we arrive. Okay.